So today I'd like to introduce the two projects. The first part is about our endothelium mimicking nanomatrix coding for stents. But this project we already have published several papers, so I'm going to just briefly summarize as a background. And the later part, I'd like to introduce our current work. Most of the work has not been published, and we are currently working on. And I'd like to introduce some of the concept and also preliminary data. So mainly we like to make tissue engineered atherosclerosis model, the ex vivo. The next couple of the background, I'm going to move quickly. So we have vascular disease, and the stent is a conventional treatment option. So bare metal stent used after 1990 has been successfully used. Now they mainly made of cobalt chrome, but the issue is that right now once you deploy, there is an instant restenosis. So after 2000, people used drug-eluting stent. The main concept is that they coat with the drug, and drug released, they can suppress the smooth cell. So they worked really well. However, the concern is that this drug not only suppresses smooth cell, but also they suppress the endothelial cell. So it leads to late-stent thrombosis. So right now, the challenge in drug-eluting stent is that how you can promote re-endothelization, and also people also found that recently inflammation is also another critical factor to affect the efficiency of the stent. So people are working on many different strategies. One is that in situ endothelization. So they try to recruit lots of the EPC and sort of progenitor cell. The main concern is that EPC population is very small, so there is a concern whether this really has a clinical effectiveness. And also, last several years, last almost 10 years, this field mainly moved toward more bioabsorber stent. And 2 years ago, the first bioabsorber stent was an implant and approved by the FDA. However, for the last 1.5 years, clinical outcome shows that there is a serious concern. So it seems that this field has been changed, and even there is a lot of argument why this bioabsorber stent is not working. And also, even we may need to go back to redesign even this PLA-based bioabsorber stent. So, however, I think in my personal opinion is that it is another critical factor is to provide multifunctional and more endothelium mimicking environment onto the surface. That's why this is overall our strategy is to provide the endothelium mimicking environment onto the surface. Then once it's working, then it can be applied to any types of cardiovascular device. So the ideal strategy is that you want to recover the healthy endothelium. Then the question is how. So we design self-assembled nanomatrix. So they have the nitric oxide produced in the donor, and they recruit endothelial cell, but also they can suppress smooth muscle and also prevent platelet attachments. This is completely biocompatible and also degradable. So as they all the tissues coming, and they can also induce the remodeling of the tissue. So eventually they can recover the healthy endothelium. Specifically, we incorporate cell as ligand, enzyme-mediated degradation, nitric oxide produced in the donor. Material-wise, we designed two different the peptide N5. So this is only the 4 nanometers. So we designed two different. One has the hydrophilic phobic and enzyme-mediated degradation on the middle, and incorporate with cell adhesive ligand and nitric oxide produced in the donor. By simply mixed, we can induce self-assembly. The diameter is only 8 nanometer, which means that if you induce coating, its thickness is just a couple of micrometer, but it consists of several hundred layers. That's why we can achieve the long-term sustained release of the nitric oxide gas. In vitro study shows that we can promote endothelial proliferation, but suppress the smooth muscle proliferation, and completely they can also prevent the platelet attachment. So together, in vitro study, we show that it's some potential to enhance endothelization while they suppress the smooth muscle and prevent thrombosis. Then we move to the practical approach. So we design, and one of the uniqueness is that our peptide amplifier, they dissolve in the water, which means that it can be applied to any different types of substrate, even the collagen or natural material, or even synthetic polymeric material without affecting any of their property. So simply by evaporation, we can induce self-assembled coating, And the clinician, they contract and also expand, and before and after, they shows a very uniform and stable coding. Then also recently, people are also very interested in how this affects inflammation. So we test two different things. One is inflammation and also vasodilation. And simply, this is a nitric oxide producing nanomatrix. They reduce the monocyte attachment. But if you add a scavenger to block the nitric oxide, attachment increase. It's a white bar shows that this is nitric oxide producing nanomatrix, and they show that they can they reduce the gene expression of the all inflammation related marker. But if you block the nitric oxide with the scavenger, then gene expression increase. And also, vasodilation study, we use the red, the version-treated artery vessel. So once you incubate with the nanomatrix vessel, the constricted vessel, they dilate because the NO is released, sustained release. So we can also maintain the vasodilation up to the 60 minutes and longer. And do some preliminary, this is the animal study. Right now, we are working on a large-scale rabbit and also pig study. So compared to we implant into rabbit iliac artery, and the control group show the restenosis. However, the nanomatrix coded group showed a very excellent patency and covered by endothelial cell. We don't see any the fibrin or the thrombus deposition. And even we quote commercially available stent graft implanted into the porcine iliac artery after 4 weeks. The cross-section shows that after 4 weeks, there was over 96% endothelization without any restenosis or thrombosis deposition. So it shows some great potential as some vascular graft application and also stent coding. That's so far we are working on the large-scale rabbit and also pig study, and we already published a couple of papers. What we're working on for the last 2 years is that because we know that biopsy stent isn't working, and also atherosclerosis is one of the main causes of disease. However, the big problem is that we don't know how. There's so many things we don't know that how atherosclerosis that happen and how we treat, and also what is underlying the mechanism. So what we're interested in is that let's make a tissue-engineered atherosclerosis model. So over the 20 years, people has been working to create a tissue-engineered vessel. So there is many different ways people use. However, still the challenge is that we want to create a really precise mimicking 3-layer structure, and also same time we want to maintain their function and also mechanical property. Then also really challenge is that it takes so long, sometimes several weeks, even that's very short. Mostly it takes also even several months. That means the question is that can we precisely control all these parameters, and also can we induce maturation in very short time period? And also eventually after that, can we induce this atherosclerosis in this vessel? So what we're working on is that we want to first design and develop tissue-engineered blood vessel, and then maintain the mechanical property and also function, and also we create develop this vessel in a very short time period. Then after that, we already developed a pulsatile flow bioreactor system, and we grow and we induce atherosclerosis model. Then if we're creating that atherosclerosis model in ex vivo, then we can use this one as a platform to study other cardiovascular device, and also we can also study to underlying mechanism of the tissue remodeling or some of the atherosclerosis. So our material, not only they can form as a coating, but also we can simply induce the hydrogel. So even this hydrogel, we can also induce a very thin kind of a sheet. So so we published several papers, so you can see. And the way is that we want to simultaneously, we encapsulate small cell and also fibroblast in simultaneously, so we can grow them to within a week. Then we can also simply see the endothelial cell. Then we can make a 3-layered structure, and we mature in pulsatile flow bioreactor system. So even controlling this blood flow, the flow system, we can also induce some kind of disease model inside of this tissue-engineered vessel. And a couple of preliminary data shows that this is small cell and fibroblast in small cell within 7 days they fully spread and start to producing extracellular matrix. So we can also put together, we can create this cylindrical vascular structure. Then we also, in the same time, we can also see the endothelial cell on the surface. This is onto nanomeric coated surface, and this is onto smooth encapsulated the gel, and smooth and also this endothelial cell, they become confluent and very uniformly grow. So we can create a 3-layer structure, and then now we're growing into the bioreactor system, and all the flow is a first-type flow, and we can precisely control this flow. So we're creating 3 layered structure. As the next step, we also did some preliminary study there whether we can induce the atherosclerosis on the surface. So this preliminary data which shows that we encapsulate the smooth cell in the nanomatrix sheet and then induce the atherosclerosis with the TNF-alpha and monocyte and also oxidase LDL. Then after 48 hours, we can also successfully induce the bone cell. This is preliminary data, but it shows that it has great potential. And eventually, we want to grow them into the bioreactor and also controlling all the flow system that we can control disease of the smooth muscle layer and disease of endothelial layer. Eventually, we can create ex vivo vascular disease model. And also, our gel has great potential to arteriovenous fistula. So compared to control group, so our nanomatrix gel, it shows a completely inhibit restenosis, and also it can be also used as a coating for brain aneurysm coil. And with Dr. Yoon group in Emory, we also deliver the iPS cell with this nanomatrix gel and show the excellent cardiac myocyte differentiation and cardiac tissue regeneration. And I appreciate our group members and all our collaborators. Thank you. I think we may have time for one quick question. Yes, Song.
Yes, thank you for a very interesting talk. So I have a question about this in vitro atherosclerosis model. So when you have these inflammatory cells perfused into the bioreactor, do they really penetrate and infiltrate into the vascular wall?
So the question is that whether we circulate these types of immune cell, whether they can attach and they can penetrate into maybe underlying the endothelial cell. So we going to the 2 different ways. One is that right now we're working on as a steady condition, so it's just a culture, and also evaluate whether they grow under the endothelial cell or whether we can induce the overgrowth of smooth cell. That's right now we are working. Then after that, once we move to the bioreactor system, we are also going to evaluate both. However, we also have another plan to induce the atherosclerosis in a steady condition, put into bioreactor. Then by controlling the flow system, we can also induce that disease model.